So we've talked about the solar atmosphere. The photosphere, that's the part of the sun that you see when you look up in the sky. And so that's the bright part. And then above the photosphere is the chromosphere. So that's also part of the solar atmosphere. It's the outer part of the sun. And it's actually the light of the star of the sun is shining through the outer parts of the photosphere and the chromosphere. And that's what gives you the spectral lines. But there's a really, really thin, tenuous part of the sun that's way out beyond both of those, and it's called the corona. The corona of the sun, you see whenever you have a solar eclipse, is this splashy sort of light surrounding where the sun is in the sky, and it's super thin. It looks like it's a lot of stuff there, but it's so thin, it's actually thinner than the gas in space above the Earth where the space station is orbiting. So it's very, very thin material. The corona is very hot. It's nearly 1 million Kelvin. But because it's so thin, if you just happen to be floating in the middle of the corona, then you would not really be getting a lot of the heat directly from you. So you'd be sitting here floating like in a spacesuit in the middle of the corona, and the way that the heat normally would burn you up would be the radiation from the heat hitting you, except it's so thin, there's not much shining on you, or the contact of it with you, except there's not much there to contact you, so you would actually not be unpleasant due to the heat. Well, unfortunately, because it is so hot, what does this mean? Heat in this case, that the hotness of it is not really a measure directly of what you think of as temperature. It's really how fast the molecules are moving. Temperature is a measure of the kinetic energy, the motion of the molecules. So here the molecules are moving very fast, or the parts of the corona are moving very fast. It's mostly made of hydrogen, uh, and and uh, and they're moving really fast, and so they will actually shoot into you. So you really get more radiation than you do anything else in particulate radiation and also X-rays. When something's that hot, it's giving off a lot of X-rays. And that's how we study it. We have X-ray telescopes that study the corona, or the outer parts of the sun. Um, there's sort of a transition region between the chromosphere and the corona, and we call that, astronomy way of naming stuff, the transition region. And so that's where the temperature increases drastically and the pressure decreases drastically. Trace spacecraft. This is a spacecraft that was launched by NASA to actually study the corona transition region. And so the idea of studying this is that you've got the photosphere, and the photosphere is what you see ordinary with the telescope. Then with an H alpha filter, then you can see the uh, um, the the uh, uh, the chromosphere, and then you can see with an X-ray telescope the part of the corona, and then a high energy X-ray telescope the outer parts of the corona. So that's what the sun would look like if you were to look at it in X-rays. Notice at the top of the picture where it's really dark up here, we call that a coronal hole. It's not really a hole in the corona, but it's a place where the corona is very, very thin and less energetic. And so it turns out that has a lot to do with how the sun affects Earth, and we'll get to that in our next unit. Okay, so there's a corona hole actually facing us. So as the sun rotates, this is a picture taken some years ago, and the corona hole was facing us. And what happened? Uh, there's the sun actually this month, earlier part of this month, and you notice it's very less active. We're at near solar minimum activity, so the sun's not very active, and so right now that's kind of what the sun looks like. Not very active, very thin corona through the middle here. You can see where it's kind of dark. So there's the layers of the sun. We've got the core in the middle. The core is where the nuclear fusion is happening. You got the radiative zone. The radiative zone is where the energy is bouncing its way out. The convective zone, where it's circulating, and the circulating gases take the heat out to near the surface. and then the so-called surface of the sun is the photosphere, and the photosphere is the part you see in the telescope. With an H alpha filter, hydrogen alpha filter, then you're able to see the chromosphere, which is the reddish region with a lot of dynamic structures to it that are above the photosphere. In this diagram, you see actually in the photosphere, you also get sunspots and granules. We'll talk more about sunspots again in our next unit. Okay, and then the outer part of the sun beyond that would be the corona out here. Trying to study the sun is tough because we're studying it from 93 million miles away, 1 AU, 150 million kilometers. And so can't really go to the sun because it's too hot. Well, I say that, but NASA did launch a spacecraft to the sun. We talked about that a little over a year ago. They launched a spacecraft to the sun, and it's called the Parker Solar Probe. And so it was launched actually about a year ago. It was launched, or a little bit over a year ago. It was launched to the sun, and it's not going to fly into the sun or land on it or anything, but it's going to fly closer to it than any other spacecraft. So in the diagram down here, the inner green circle there is the orbit of Mercury, and so it's diving much, much closer to Mercury, to the sun. And so over the next few years, then it's going to be in closer and closer to the sun. In the graph up here, the blue line up here, that marks the distance from the sun. And you can see over the years, it's going to be getting closer and closer to the sun. The closest to the sun will be actually in the year 2025. In order to survive getting that close to the sun, the spacecraft actually has a special carbon composite heat shield that protects it, and solar panels that will actually fold up behind the heat shield to keep them from being vaporized by the sunlight. So once you're very close to the sun at perihelion, the closest, it's going to be over 2,500 degrees Fahrenheit, and so that would actually melt the spacecraft. This picture right here actually shows how big the sun appears from Earth compared to how big it appears from the Parker spacecraft when it's close to the sun. And so, in fact, it's actually going to be flying close enough to the sun, it's going to fly through the outermost parts of the corona and give us our first up-close measurements of exactly what the corona is like. It's already passed a couple perihelions, not the closest perihelion it's going to get, but it has passed a couple to the sun and been right at the edge of the corona. And the corona looks like that. Actually, the corona looks nothing like that, so we'll just kind of forget that. Okay. All right. So, the Ulysses spacecraft. One of the other problems that we have studying the sun is we're looking 1 AU away, and Earth is always looking down the equator of the sun. Earlier, when we started talking about the sun before spring break, I said we actually had a spacecraft that flew out to Jupiter, let Jupiter's gravity toss it into an orbit that was going around the sun, perpendicular to it. So the Ulysses spacecraft got to actually see the north and south poles of the sun. Well, the other thing about the sun I want to mention here is physicist by the name of Ludwig Biermann noticed that when you look at a comet, as a comet goes around the sun, the tail of the comet always points away from the sun. And it kind of wiggles and waves as if there's something pushing on it. So he came up with the idea there's like a wind of particles coming from the sun. Well, astronomical way of naming such a thing, we call it the solar wind. And so it's a stream of particles coming from the sun, mostly hydrogen particles, protons or some electrons. And so as they fly away from the sun, they're sometimes thicker and sometimes thinner. And so as they go past Earth, we talk about the solar wind and gusts and so forth. And this is almost like weather. In fact, it does affect the environment of Earth. We call it space weather. The north and south poles of the sun almost always have coronal holes, and those holes allow more solar wind to come through. And that really affects things because when there's a coronal hole facing Earth, we get more solar wind. And this, again, affects the space weather. That affects radiation loading of Earth, affects radiation if you fly, affects cosmic rays, and so forth. more solar wind has a substantial impact on Earth. And so when the sun is in lower activity and the corona is not as active, you actually have more solar wind, which is kind of converse to what you would think. Okay, so with that, we'll kind of like have pause this for a little bit, and the next unit we talk about is going to be solar activity. Everything we've been talking about so far is about what we call the quiet sun. If you can imagine big blobs of gas the size of Earth coming to the surface, popping and sinking in about 5 minutes, or blobs the size of the Earth, coming up and down over several hours, that makes the supergranules. The smaller blobs make the granules. All this other activity like the solar wind and all that, that's considered the quiet sun. And so we're now about to embark on a study of the active sun, and that's what gives rise to space weather and solar storms. So that's going to be our very next topic.